start now, sir?
Yes, first just explain me your title and your motivation for this research.
Okay, sir. Okay, good morning, sir. Myself Asha JK. So I'm here to present a pre-PhD Viva presentation. So my topic is a study and characterization of single domain nano-crystalline hexaferrite magnetic nanoparticles.
Okay.
So here are
what
the
exactly this research you want to do in nanoparticle?
Sir?
What exact research you want to carry out in the field that I know over in your title, and give me the motivation why you picked this title.
Sir, here I am focusing on understanding the synthesis, properties and applications of magnetic nanoparticles in a various fields like physics, chemistry and biology and different medicine fields. I am going to study the synthesis and properties of properties and applications of magnetic nanoparticles, sir.
Okay. So, do you have any research setup for this?
Sorry, sir. Your voice is
not clear. Do you have any
clear.
research? I'm saying, do you have any research setup for the same?
Research?
Research setup. Do you have a research setup to investigate the nanoparticle behavior?
Sir, I studied theoretically only, sir.
So you do not have any experimental evidence with you?
Sir, I have some experimental evidence like this, sir. These are the synthesis process to provide nanoparticles in a monodisperse method.
Have you done your own synthesis or not? I'm asking that. Have you done any experimentation by your own or not?
Yes, sir, I have done.
Yeah. So which lab you had used for this? Where is your lab? Your laboratory name?
Sir?
Your laboratory name. Where your laboratory is, in your university, or you have doing these things somewhere else?
Sir, in university only I have done, sir.
In university you have done. Okay. So which type of instrumentation is required for synthesis of nanoparticle?
Sir, I used this transmission electronic microscopy images method and monodisperse of nanoparticles method.
Okay. So which microscope you had used?
Sir, transmission electronic microscopy.
Okay, transmission electron microscope you had used. What was the resolution of that microscope?
The resolution.
Okay, go ahead with your introduction. We will discuss these things in your research methodology again.
Okay.
Okay.
So here is a small introduction about the nanoparticles. So nanoparticles are the tiny particles or materials with a dimension ranging between 1 to 100 nanometers. And they can compose 100 to 1000 atoms. And the magnetic behavior is a response to magnetic fields varies by the type of ferromagnetic, paramagnetic, ferrimagnetic, superparamagnetic, and etc. And an introduction for a magnetite, that is Fe3O4 nanoparticles are they have high magnetic moments, biocompatibility, chemical stability, and they have a wide range of applications in the field of medicine, catalysis, batteries, and water treatment, extra.
Yeah.
So here is a method of monodisperse of nanoparticle, synthesis of monodisperse of nanoparticle. Here we are using injection of reagents at a high temperatures. We are injecting reagents to a surfactant solution. So here surfactant which is used is which stabilizes the nanoparticles and controls the growth. So after some time, it is aging and produces a different sized nanoparticles. Here, many small nanoparticles and large number of nanoparticles are produced after the process of aging. So after this process, size selection process is going on, and after the size selection process, we get a different size of nanoparticles with a monodisperse method. Monodisperse method. And the second figure, this one explains the transmission electronic microscopy images of magnetite nanocrystals. Here we are using a high temperature method. We are using high temperature method. Here a solution is a concentration of iron oxide with in the presence of this carboxylic acid and that is ODE. ODE means octadiene. Okay. After a high temperature method, it produces many number of nanoparticles that are randomly oriented. And further heating, the process is continuation. Further heating, it produces a large number of nanocrystals which are having a same size, that is a monodisperse, same size. It produces a many number of nanocrystals having a same size. And here this figure explains illustrates the Lammer model, and this small figure, this explains the hot injection setup to achieve the burst nucleation. So this Lammer model explains the different steps, that is injection method, nucleation method, and growth from a solution, post-wall refining, and a saturation method. So in the first one, injection and nucleation, burst nucleation takes place. That is a precursor concentration increases rapidly due to the reagent injection. Here, due to this injection method, many number, that is rapidly increases the number of nanoparticles. So after which reaches the nucleation threshold, it falls down and a growth phase takes place. After the nucleation, the concentration drops below the nucleation threshold. And here existing nuclei grows as more material deposits on them. And in a third phase, post-wall refining takes place and saturation takes place. So in a post-wall refining, here what happens is small particles dissolve and contribute to the growth of larger ones, leading the more number of nanoparticles and size distribution takes place. So here after the post-wall refining, smaller particle dissolves and gives a larger particle growth of the larger particles, so that we get a large sized nanocrystal. And here the second image, which explains hot injection synthesis setup. That is hot injection synthesis setup. Here injection takes place due to which high nucleation takes place. No, so this explains that hot injection synthesis setup. Here, which explains. Here, commonly we used to achieve a burst nucleation in a nanoparticle synthesis. The solution is injected using a here the solution is injected using the syringe into a flask that containing a hot coordinating solvent and a stabilizer. And here a thermometer which monitors the temperature to ensure the controlled conditions. So in this method, rapid injection leads to a instantaneous nucleations followed by the producing a uniform nanoparticles. So these two explains, the first one, Lammer model explains to achieve the monodisperse nanoparticles through the burst nucleation and a controlled growth. And here this one, second figure, this explains the hot injection synthesis, which is a widely used technique to ensure the rapid and uniform nucleation, leading to a high quality high quality of nanomaterials or nanoparticles. And this is the figure this illustrates which illustrates the behavior of magnetic dipoles in different types of magnetic materials like diamagnetic, paramagnetic, ferromagnetic, ferrimagnetic, and antiferromagnetic. So in case of a diamagnetic material, what happens is when there is no magnetic field, dipoles are randomly oriented so that it shows a no net magnetization. But in the presence of the magnetic field, what happens? The dipoles align slightly in a opposite direction to the direction of the magnetic field. So here the magnetic field is in this direction, but the dipoles arranged are in a opposite direction. So it leads to weak negative magnetization. Next, in the case of paramagnetic materials, when there is no magnetic field, dipoles are oriented randomly. When there is no magnetic field, dipoles are oriented randomly. And in the presence of magnetic field, dipoles are aligned in the direction of the applied magnetic field. So here the magnetic field direction is this one, and dipoles are arranged in the same direction. And after removal of the magnetic field, soon they come to a original state, that is again the align in a randomly orientation. Next, in the case of ferromagnetic materials, when there is no field, they are already arranged in the same direction. Dipoles are arranged in the same direction due to the strong internal interactions even without the external field. When there is a field, the alignment strengthens and leading to a strong magnetization in case of what? Ferromagnetic materials. Next, in the case of ferrimagnetic materials, when there is no external field or when there is no magnetic field, the dipoles are aligned in an opposite direction with a different magnitude. And with the field, the net magnetization increases. Next, in the case of antiferromagnetic material, when there is no external field, the dipoles are arranged in the opposite direction with the same magnitude. Here in the ferromagnetic materials, magnitudes are different and the directions are opposite. In the antiferromagnetic material, magnitudes are same and directions are also opposite. So we can conclude that there is no net magnetization as the opposing dipoles cancel out each other. Okay, this is what anti-ferromagnetic materials. So next, this is a figure which represents the magnetization behavior. This red line indicates ferromagnetic, green color indicates the super paramagnetic, blue color is a paramagnetic, and this black line indicates a diamagnetic properties. So first one, in a ferromagnetic, this red color line, this ferromagnetic behavior which exhibits a hysteresis loop, that is this bold curve. Hysteresis loop shows the magnetization when external field is removed. And in a super paramagnetic, this is a green line, which is similar to ferromagnetic but does not exhibit a magnetization. And a paramagnetic behavior, this blue color line, which exhibits a linear response with the field. And last one, that is a diamagnetic material here, which shows the weak, and in a diamagnetic, I already told there is a weak magnetization. So this line shows a weak magnetization, weak and a negative magnetization. So the conclusion of this figure is ferromagnetic materials have a strong magnetization, and super paramagnetic materials behave like a ferromagnets and lose the magnetization when the field is removed. And third one, that is a paramagnetic materials, they have a weak and temporary magnetization. And in case of diamagnetic material, it material shows a weak and negative magnetization. So this is what the figure, the loop explains. Here we have a magnetization. In the x-axis we have a different magnetic field. In y-axis we have a magnetization. So the next thing is magnetic nanoparticles. So magnetic nanoparticle, here we are focusing on development, behavior, applications in biological sciences, and they have a wide range of applications in magnetic drug targeting, MRI, hyperthermia, tissue healing, and different fields. And there is some size effects, that is high surface area and a reduced sedimentation rates are advantageous. Size dependent properties like super paramagnetism. And the next thing is nanomaterials and nanotechnology. So here a rapid growth, that is expanding fields in the material science, including condensed matter physics, biology, medicine, and electronics. And the next thing is a multidisciplinary approach that involves biologists, engineers, and physicists. Nanoscale definition, that is a materials with the morphological characteristics smaller than 1/10 of the micrometer. So next, here is a image that contains two figures. So first one is experimental strategy for estimating a blocking temperature of magnetic nanoparticles. And here next one, a qualitative illustration of the behavior of the corrosivity in ultrafine particle systems as the particle size changes. So first one here FC means it is a field cooled curve. It represents the magnetization measure when the sample is cooled under the applied magnetic field. It is a sample is cooled under the applied magnetic field. And the second one is zero field cooled. That is this curve represents the magnetization measures after cooling the sample without magnetic field. Here first one is with the magnetic field, and the second one, this zero field cooled, this refers to what? Without magnetic field, the cooling the sample. The intersection of these two curves, FC field cooled and zero field cooled, intersection of these two curves defines the blocking temperature. That means here it is TB, blocking temperature, which separates super paramagnetic and a ferromagnetic behavior. Super paramagnetic and a ferromagnetic behavior. Below this blocking temperature, nanoparticles exhibit a stable magnetization. Below this blocking temperature, nanoparticles exhibits a stable magnetization, and above the blocking temperature, they become super paramagnetic and lose the magnetization.
Asha ji, please,
Yes,
this
sir?
is all theory. Come to your work.
This is an introduction, sir, which helps to complete my work.
This is all theory. Could you please give me what research publication you had considered? Show some literature survey first.
Yes.
Have there any base paper?
Yes, sir.
Yeah, what are your objectives? Yes, show this also.
So, sir, here is the objectives to investigate the synthesis methods and to characterize the magnetic properties, to explore the coating materials, to assess the applications, and to address the research gaps.
These are your objectives.
Yes, sir.
What is the new thing you are carrying out from here? As per your objective, what you are doing, basically simply reading others' research or access the others' research. What exactly you did new? That's my question from very first slide. What exactly new thing you bring in this subject?
Sir, here we are investigating a development and behavior of magnetic nanoparticles, understanding their magnetic characteristics, and exploring the potential applications of hybrid magnetic nanoparticles.
Which particular material you are using? Which particular the nanoparticle means all belongs to ferrous group. So which particular ferrous that is you had used? As you mentioned, the hexaferrite. That is in your title, na hexaferrite.
Yes, sir.
Okay, so beside other than hexaferrite, are other nanoparticles are available or not?
Available, sir.
So why only hexaferrite you had picked for your research? Why not other? What are the key advantage of hexaferrite over others? Yes, Asha ji.
Yes, sir. Hexaferrites have a high magnetic. They have high corrosivity, sir.
High corrosivity is not in your favor, na?
And they have a thermal stability, chemical stability.
Other are not having the same thing, same parameters or same quality. You have to prepare a comparative chart why you are picking hexaferrite for your research, why not other ferrous elements you are considering, ferronanoparticles are considering for your research, that you have to be mentioned and discuss. Okay.
Okay, sir.
Which type of, as you are saying, you are looking for the coating material. Which type of application other than coating are possible with the ferrous nanoparticle or magnetic nanoparticle?
Here we are using a magnetite nanoparticle, sir, that is Fe3O4.
Where you can use this magnetite nanoparticle? Applications. What are the applications of this?
Sir, applications of this magnetite that is Fe3O4 is which is used in production of ferrite cores of transformers, inductors, electromagnetic devices, which are used in a catalysis and in biomedical applications.
What type of biomedical applications?
Sir, in case of MRI, that is a magnetic resonance imaging,
Yes.
nanoparticles of magnetites are used to enhance the scannings in MRIs. And
These are
hyperthermia
injecting in a
is
human
used
body.
in the cancer treatment.
Are they injecting in human body?
What, sir?
Are they inject in human body?
Which one?
Your ferromagnetic particle are injected in a human body for better
No, sir,
analysis.
they are not injecting.
What they are using in MRI? How they use in MRI to increase the image? enhance the image quality.
During scanning, sir.
How? The magnetic field create in the MRI machine using electromagnetic field they had generated. Okay.
Yes.
What is the use of this nanoparticle over there? Exact use of nanoparticle. I don't want a general answer. You are a PhD scholar. Okay.
Sir,
Anybody else in
magnet.
present is doing the research in the field? The
Sir,
present
the
researcher and
case
what
of
type
super
of research they are?
paramagnetic behavior, super paramagnetic behavior of the nanoparticles,
Hmm.
which strongly interact with the external magnetic field.
Hmm.
That property helps to get a clear scanning in case of MRI.
Wait, that's I'm asking now, where these particles are in machine or in human body?
In machine, sir.
In machine, so how they are giving good images of that?
Because of super paramagnetism that is at the nanoscale.
Okay, go ahead
That
with
means
your
they
literature.
strongly interact with the external magnetic field, but do not retain magnetism when the field is removed.
Okay. Move to the next your slides, like research methodology.
Here is a research gap, that is identification of ferrite nanoparticles possess unique properties that makes them useful in biomagnetics for applications like drug delivery and sensing. Existing methods are co-precipitation method and a microemulsion method. They have limitations in terms of size, control purity, and a uniform of nanoparticles. So what is the need to improvement is enhanced control over a nanoparticle size, composition, and morphology, development of a more efficient synthesis methods that offer better reproducibility and scalability. Here, mapping of objectives to the research gap. The objective is to develop the hydrothermal synthesis method for producing ferrite nanoparticles with a controlled size and a composition. And addressing the gap is the proposed method aims to overcome the limitations of our existing methods by allowing precise control over the reaction condition and the surfactant use. And characterization techniques used are X-ray diffraction, that is XRD method, TEM, transmission electron microscopy, and SEM, scanning electron microscopy, and electron spin resonance spectroscopy, atomic pair distribution function analysis.
Is XRD available in your university?
Sir?
XRD facility available in your university?
Yes, sir, it is available.
I don't think so. What type of machine it is? How it is work? Have you ever seen the XRD machine? XRD setup?
No, sir.
At least search these things on web before going for Viva. What type of XRD is, availability of XRD with your university or nearest institution. Like in Bhopal, it is available only with MPRI. Okay. And MNIT
Can you
Bhopal.
repeat, sir?
It is available with the MPRI and MNIT Bhopal. No other and ISSCR Bhopal. 3 institutions only have this machine in Bhopal.
Okay.
Okay. Not
Okay, sir.
not a single university, even though in Barkatullah University, Mansarovar Global University, and others don't have this facility.
Okay, sir.
Okay, the peoples are taking their sample to Ampri and taking the results from there only.
Okay.
So whatever the equipments and machinery you are using, you have to first of all identify where they are actually and what their specification, what type of testing they are doing.
Okay, sir.
Okay, how to prepare a have you any idea how to prepare a nanoparticle specimen for experimentation over XRD?
No, sir. In theory, I studied.
Okay, move ahead.
Here, methods and materials. Ferrite nanoparticles are of interest due to their unique optical, magnetic, and electrical properties. Magnetic nanoparticles are used in biomagnetics for drug delivery and sensing. Wet chemical methods allow for a precise control of ferrite nanoparticle composition, microstructure, and size. The chapter covers the magnetism theory, dielectric phenomena, and instrumentation details for characterization techniques like XRD, SEM, and TM. Here, metal precursors are cobalt chloride heptahydrate, zinc chloride, uh, copper chloride, and a copper nitrate trihydrate, magnesium boride, magnesium sulfate, magnesium nitrate, nickel, sulfate hexahydrate, nickel acetalcinate, nickel chloride hexahydrate, nickel fluoride, nickel oxalate, magnesium chloride, iron chloride, tetrahydrate, and etc. Here, this figure explains the Bragg's law, incident X-rays, and here which gives a diffracted X-rays. And this figure which illustrates the signals generated from a specimen by electronic beam. And this gives the schematic diagram of the transmission electron microscope. So, come to the X-ray diffraction, that powder samples prepared from the sonicated slurries in ethanol, analyzed using syntact diffractometer with the CU radiation, data analyzed using a Bragg's law and Debye-Skerrer formula for particle size, and in case of TEM, uses of electrons for high resolution imaging of samples, images and diffraction information collected using a Philips CM200. And in case of SEM, which offers a high resolution for surface study, interaction of electron beam with the sample generates various signals. And electron spin resonance spectroscopy, which measures magnetic properties using an interaction of unpaired electrons with an external magnetic field, and data collected with the JOL model and FA100 ESR instrument.
These are the Ashaji, the Philips ESS and JOL model. These are the machine or equipment name that you have to search on internet what exactly these models are and other details of these things. Okay.
Oh, okay, sir. Okay.
Without maybe possible, your examiner may ask other specification of these machines.
These machines. Okay, sir.
Okay. So please do, and also learn how to prepare your specimen. Okay.
Okay, sir.
For scattering and other parameter for the testing on these machine, how to prepare a specimen and what number of specimen you had prepared. They may ask you how many specimen you had prepared and what the things are. Okay, so please mention those things also, or please learn those things also.
Okay, sir.
Okay.
Okay, sir.
Next.
So here magnetic data collected on the ferrite nanopowders encapsulated in the paraffin wax. Atomic pair distribution function analysis. Here we conducted using a synchrotron X-ray data and ePDF method, Excel data processed to obtain the PDF and structural models. Preparation methods of hexaferrites that techniques include sol gel process, solid state method, salt melting, ball milling, self-propagating, high temperature synthesis, chemical co-precipitation, and microemulsion route. Importance of this co-precipitation method, which is used for synthesizing ferrite nanoparticles, which involves a co-precipitation of a metal hydroxides followed by the ferritization. Next, microemulsion or reverse missiles is a thermodynamically stable dispersions of aqueous and hydrocarbon liquids. Reverse missiles used for a nanometric scale particle synthesis via precipitation or reduction reactions. So next thing is analysis. Here conductivity measurements CPN versus CPT. Here CPN shows lower conductivity values compared to CPT. This is likely due to absence of a surfactant VAT, which increases ionization and conductivity. And CPT higher initial conductivity and higher final values suggests that surfactant enhances the reaction efficiency, leading to more complete reactions. Next one, precipitation effect. Addition of the ammonia decreases conductivity in CPT due to the ion reaction and a reduction in free ions, while CPN maintains or increases the conductivity, indicating ongoing ionization. Next thing is a ME sample. Here conductivity initially increases with the metal salts and oil phase, but decreases with the NaOH addition due to the ion reaction. The final conductivity is minimal, indicating high stability after saturation. So these are the figure which illustrates a DC conductivity measure during metal salts addition to DI water, and the second one, ammonia addition to a metal salt solution for samples of CPN and CPT. And this figure illustrates conductivity of solutions, water phase, oil phase, while mixing a water into oil and adding a NaOH. And here, this explains the DC conductivity of metal nitrates added to a DI water. And the second one, that is the addition of citric acid into metal salt solution. And the third one, during the precipitation with the NH4OH. And here, this curves a sample of CPN and CPT. And this is a curves sample for MER. So this is the spectra for samples SN and ST heated microwave and 950 degrees Celsius. This is what a XRD pattern for samples of a CPN and CPT calcined with different conditions. And this is the figure which illustrates a XRD pattern for the samples SN and ST with different conditions, and XRD pattern for a sample ME with different calcination conditions. So next thing is a FTIR analysis, CPN versus CPT. Here CPN broad OH band presents at a lower temperature, which disappears at a higher calcination, indicating a loss of OH groups. And in case of CPT, similar metal oxygen bands with additional bands due to the surfactant, but these disappear at a higher temperatures. And in case of ME sample, OH stretching and HOH bending vibrations are prominent initially, but decrease with the heating, indicating water evaporation. Metal oxygen bands become visible with the further heating. And SN versus ST, in case of SN, which shows the bands corresponding to nitrate and a surfactant, which disappear at a higher temperatures, revealing FeO stretching vibrations. In case of ST, similar pattern with additional surfactant bands at a lower temperature and FeO bands at a higher temperature. In case of XRD, CPN lacks crystallization in as precipitated state but shows M phase peaks after high temperature calcination. And the CPT shows the impurity peaks at a lower temperature but purifies at a higher temperature. In case of ME sample, no crystallization initially, but a clear M phase formation at a higher temperature with the broad peaks indicating a nanoscale particles. SN versus ST, SN shows a pure M phase with a good crystallinity. In the ST, which also shows a M phase with a more pronounced peaks indicating better crystallinity and phase purity. This is a table which explains the lattice parameters A, C and unit cell volume V derived from the XRD patterns of SrFe12O19 hexaferrites prepared for the series 1, which are the different curves, different graphs, empty curves for SN and ST samples.
Asaji, I am not able to see your screen.
Screen is not visible, sir.
No.
Is it visible, sir, now?
Yeah, now it is visible.
So next thing is the Curie temperature measurements. The lower Curie temperature compared to SN and ST suggesting a less effective preparation method, and in higher Curie temperature which indicates a more effective preparation and potentially better magnetic properties. Next thing is the dielectric measurements. In a CPN 950, high dielectric constant at a low frequencies, decreasing with the frequency indicating the space charge polarization. In the ME samples, rapid increase in a dielectric constant at a low frequencies with a peak observed for a samples heated to 500 degrees Celsius, indicating Maxwell-Wagner polarization. In SN and ST, two types of behaviors are observed. First one is a traditional dispersion for some samples. Increased dielectric constant with the frequency for ST, MW suggesting collective contribution to polarization. So here is the figure which explains SEM images for samples ME calcinide at a microwave frequencies and a 950 degrees Celsius. And this is a graph which explains a particle size estimation for samples synthesized by using different methods. And this is a loop, hysteresis loops for the samples of CPN 950 and CPT 950. So these are the tables which gives the percentage size distribution over the particle size with the different calcination conditions. And this is a table which gives, which represents the magnetic parameters of SrFe12O19 hexaferrite samples prepared with the different chemical routes. Next thing is the SEM analysis. Here general observations are samples are prepared via microwave treatment. Show uniform spherical nanoparticles. Surfactant helps to control the particle size and shape, leading to more uniform particles. Next thing is the particle size distribution. Particle size distribution varies with the preparation methods and sintering conditions. Lower calcination temperatures can lead to finer grains, which are desirable for high frequency applications. Next, here are some findings. First one is a zinc substitution, which increasing a zinc concentration improves the saturation magnetization and a specific absorption rate, that is SAR, making the material suitable for applications such as magnetic drug delivery and hyperthermia. Second thing is a magnesium ferrite synthesized using sole gel and co-precipitation methods. These ferrites shows the single phase cubic structures with the varying magnetic properties depending on the doping and the synthesis method. Third thing is strontium hexaferrites achieved pure hexaferrite particle with enhanced magnetic saturation and low corrosivity through optimized synthesis and annealing process. Hydrothermal method. This method produced various ferrite nanoparticles with tunable sizes and compositions, demonstrating potential for photocatalysis and catalytic applications. Next is a result, that is a product characterization, size, composition, and morphology. Here a detailed synthesis of various ferrite nanoparticles and characteristics, XRD analysis, which uses structural data, crystal size and lattice parameters, TM analysis, shape and size distribution. SEM studies gives details on the surface morphology and particle uniformity. And next thing is a magnetic characterization. Here, SQUID squid magnetization analysis, magnetic properties of CO-Fe2O4 nanoparticles at different temperatures, and a magnetic ordering and hyperfine parameters of various ferrites. So here ferrite synthesis and properties. Here Ni-Zn ferrites, nickel zinc ferrites successfully synthesized using a sole gel and a non-aqueous methods. The non-aqueous method facilitated rapid low temperature production of nanoparticles. And next thing is the doping effect. CO2 plus doping improved magnetic properties, including a higher saturation magnetization and a specific absorption rate, that is SAR. Increased zinc concentration led to an enhanced saturation magnetization and a specific absorption rate with a low corrosivity observed at a high zinc level. And next to magnesium ferrites synthesized via sole gel and co-precipitation methods. XRD analysis confirmed a single phase-centered cubic structure. Particle sizes were smaller in CO3 plus substituted samples compared to Cr3 plus substituted samples. Next is strontium hexaferrites produced using precipitation with the surfactants, resulting in a pure hexaferrite particles with a minimum magnetic saturation and a low corrosivity when annealed at 850 degrees Celsius. Next thing is a hydrothermal method which is enable the synthesis of various ferrite nanoparticles with the controlled sizes and compositions. Ultra small nanoparticles less than 4 nanometers exhibited superparamagnetism and varied magnetic behaviors based on size and composition. Here magnetic and structural properties. Here doping in the doping process increased doping concentration, improved magnetic properties with high magnetic moment and positive magnetocrystalline anisotropy energy, contributing to enhanced saturation magnetization. Next, magnesium ferrites displays broad symmetrical signals indicating paramagnetism. Saturation magnetization values were affected by co-doping, showing reduced values at a low concentration but increased values with a high CO doping. Strontium hexaferrites, which achieved...
What is your final conclusion, Asha ji? Final conclusion. Have you justified your all objective?
Yes, sir. Here, objective enhance the magnetic properties of Ni-Zn ferrite nanoparticles through doping, synthesis methods, and annealing temperature. And we get the results. Doping improved magnetic properties such as higher saturation magnetization and a specific absorption rate, increased zinc concentration, enhanced MS and SAR, but reduced corrosivity at higher levels. Non-aqueous synthesis method allowed for a lower temperature, rapid production of nanoparticles with the improved magnetic. And one more objective is to investigate the structural and morphological and magnetic properties of ferrite nanoparticles using various characterization techniques. A result we get is a structural properties confirmed through XRD method, showing single phase formation and a phase centered cubic structure for ferrites. And in case of TM and SEM analysis, which provided detailed insights into the particle size and morphology. Next, magnetic properties analyzed using VSM, showing improved saturation magnetization and specific absorption rates with variation attributed to doping levels and particle sizes. Next
Okay.
objective is to develop and validate a new synthesis method for ferrite nanoparticles to optimize production conditions and properties. Result we get is a non.
Asha ji, Asha
Yes,
ji, what I had observed for your whole presentation, as you say, initially you did a theoretical work. It's not a theoretical work at all. It is a an experimental work was it is. Okay. So
okay.
first, the main thing that you have to be considered that, as I already told you, to identify the resources where you conduct all the experimentation, and if possible try to fetch some figures of those machines, and even though some experimental setup, if you can visit and understand how to prepare a specimen, how to use those, how to check those specimen, and how many specimen you require for testing all those things, how you conduct the
Okay.
doping and all. So you have to understand all these process before presenting your work in front of anyone, because in your conclusion, in your objective, in your experimentation, in your research methodology, everywhere you are explaining the
Practical
what I
things.
say, a practical thing, and you are
Yes.
saying you are did a theoretical thing. I understand that in actual practice you didn't go for any type of experimentation, but when you go for the actual presentation in front of your examiner, na, so then you required to answer these things. So
Yes.
beside the
Yes.
general questionnaire, what was the motivation behind of your research? What type of base paper or what type of current research is going in your area? Why you pick this area for your research? What type of machinery you are using? You have to understand the exact experimental or research approach for your work. If you fail to explain that, no, so then it will be create a problem. And examiner may ask you, you do not do any type of research, so how could you? Why should I pass you, or why should I clear your work? Okay, so just
Okay, sir.
understand the experimentation part, doing it a survey on internet and somewhere else, understand the process, how take use Google or so what is say YouTube for understanding the lots
Yeah.
of the process, where how to use STM or TM and your XRD and all. Okay, go through
Okay.
their
Okay, sir.
videos on available on YouTube and all. Okay, before that will be help you to prepare for your Viva. Okay,
Okay, sir. Okay, sir.
okay, rest is good. No issue with that. Okay. All
Okay.
the very best.
Okay.
Bye bye.
Thank you, sir. Thank you very much, sir.